There we go. Current production. We've looked at cells a little bit before and we discussed this, that things will move from high to low potential. This goes for gravitational potential or any other potential energy. In this particular case, we have a situation where electrons will flow from a low potential from high to low, essentially. They will flow until the potential is equalized. What this really means is we have a current flow, a net movement of electrons in a certain direction. And what that means is a certain number of coulombs of charge will pass per second through some space in a circuit. And that's measured in amps. And as we've kind of said before, batteries are really electron pumps. Later on, we're going to refer to them as an electromotive force. That could also mean a generator, but a battery is a form of electromotive force. And what it means is it sets up a potential difference across your circuit. If you want to run electricity through anything, attach one end to a positive terminal, the other end to a negative terminal, and your power will basically run through your circuit. It'll go from high to low potential. So when we're looking at our batteries, here we've got a system where they give a potential difference. You can have wet cells, you can have dry cells. We talked about batteries a little bit before. The actual chemistry of these things, something we're not going to get into. Ask a chemist about those. I'll talk to them about them a little bit about the history. But what we care about is when we hook wires across these terminals, they make a potential difference that causes electrons to move. Okay. And when the electrons move, what they're actually doing is they're doing useful work. In this particular case here, the electrons are moving through this bulb. These old type bulbs that used to have a filament and were a lot easier to find at one time of day means that as the electrons pass through, the increased resistance in this filament causes it to put out heat and put out light and glow, especially when it's in some kind of noble gas such as neon or argon or whatever. As the electrons move, they do work and they convert their electrical energy, their potential energy, into electrical energy, essentially. Here is resistance. So, in generating electric current, as I said, you can have an electrochemical cell, which is what we were just talking about, which is a battery. It changes chemical energy into electrical energy. You can have a thermocouple. This is the kind of thing you get in temperature style devices that for taking temperature right now with medical use, amazingly enough, or thermal sensors on most cars and other equipment will use a thermocouple system, and that really uses a electric current to tell you what the temperature of a system is. The resistance of the object will actually change based on temperature and allow more or less current through. And finally, you have generators. And here, it says reverse of an electrical generator. It should say reverse of an electrical motor. And these provide an alternating current. We'll get to AC later on, AC and DC systems. So don't worry about that. The systems we'll deal with for quite a while here are going to be DC systems, which tend to be the output of an electrochemical cell. So like I said, you can have a DC or an AC current. DC is what we're really dealing with here. All the electrons in a DC system flow the same direction in a wire, and they're a flat waveform. They do not vary. An alternating current system, by contrast, has electrons that flow two different directions in the wire. The output fluctuates, and this is the kind of thing that's coming out of the outlet of your home. And you need a transformer, not the kind of plastic toy robots that we are used to seeing, but an actual electrical transformer to take alternating current and make it into direct current to power things like computers, so that they don't have some varying power input to them. We will talk about that in more detail as time goes on. But a couple of definitions we've already seen before. Current, which is the measured in amps and is the amount of charge per unit time which passes by a point in your circuit. And you have voltage, which is our measure of potential, which amazingly is measured in volts. V and A, these are the units. The higher the voltage, the more work an electron can do in your system. So the voltage is synonymous to, say, the pressure in a pipe pushing a water wheel. Higher pressure water is pushed through, the faster it'll turn a wheel, the more work it will do. The only other thing we really want to form right now, we really want to talk about, is resistance. And this is sort of a retarding force which holds back the flow of electrons. And that's measured in ohms. That's the symbol for that is the Greek letter omega here. This was invented by George Ohm, essentially. Lovely last name, very concise. But anyway, the Greek letter omega is used for ohms, and it isn't the Lululemon symbol. Thicker wires give you less resistance, longer wires give you more resistance. Okay. We also have a situation where conductors, if we talk about conductors and insulators, we talked about conductors before in terms of wiring. A conducting system will have low resistance. An insulating system, which holds on to electrons, doesn't want them to come through, is high resistance. So why am I telling you about this? Well, Ohm's law. We just defined voltage, we defined current, and we defined resistance. And put them all together, and you have a definition we saw briefly before, which is V equals I times R. That's an I. Okay. This is voltage is equal to current times resistance. Resistance is always in ohms. And there's a resistor. They come in all sorts of shapes and colors. We see these things less and less. Capacitors, resistors tend to be replaced by current controlling circuit boards, printed circuit boards, automatically soldered circuit boards. If you open up your computer, you're less likely to see these kinds of devices, but open up an old radio, it'll be full of these. Open up a transformer or other electrical components, and you will find these inside. The colors and the different banding actually indicates the tolerance, how much resistance you get from each of these resistors. Anyone who goes into electrical engineering will see such a thing and will actually have to identify all these different colors. You may actually do that in lab. In this class, I'm not going to ask you to identify all those colors, but just know what the colors do represent. But any object has some kind of electrical resistance, and you can think of that as a sort of narrowing of the pipe if you're looking at a water system. And we can use them to regulate voltage, regulate current, and we're going to do a lot of calculations of this later on. And that's how we really control all of our electrical systems in the world, by changing the resistance of the system. So we just defined voltage is equal to current times resistance. The other definition we want to look at is what is power. So power is the rate at which our electricity can actually do work. How quickly can it provide energy? And that comes from power being voltage, remember this is our potential difference, multiplied by current. And this is a power. And if you cast your mind back to Physics 1 and think about power in terms of a mechanics definition, power was defined as a joule per second, which is a watt. So a 40-watt light bulb is essentially doing 40 joules, consuming 40 joules of energy every second. The last definition, which is one we've seen before, is I equals Q over T. This is current, this is the charge passing a point in your circuit, and this is time. So those are the definitions we really want to hold on to. V equals IR, Ohm's law, is one of the most important definitions that you'll return to time and time again. It's about as important to electricity as F equals MA was to mechanics, in my opinion. One last one, and this is the formula for energy, and energy is equal to power multiplied by time. Okay. So that's it. Energy, power, P equals VI, E equals PT. The SI for unit for energy, of course, is a joule. Just talked about energy very briefly. If you go outside and look at your electricity meter, you'll probably notice it says something like kilowatt hours on it. If you think about it, kilowatts, well, that's a power. You know, we said before, that's joules per second. So if you take that and multiply it by hours, what you're essentially getting back is an energy. I think that the electricity companies really wanted it to relate to how much power people were using in a certain time frame, so they chose to use the kilowatt hour. But there we go, not actually a unit of energy, a unit of power, essentially. So when we're talking about current, here's a brief aside on the effects of electrical current on the body. Quite often you see big signs that say danger 50,000 volts. The voltage doesn't particularly matter. You can take a very, very high voltage, at least your body can take an extremely high voltage, but you can't take much current. Please ignore this page number, this is from an old book. You can't take a lot of current. So here 0.001 amps of current is enough to give you a mild tingling. 0.005 is pretty painful. Sticking your finger into an electrical outlet is somewhere around here. Involuntary muscle contractions at 0.01 amps. By the time you get towards sort of 0.015 amps, you're losing muscle control, and then 0.07, you're basically dead if you're exposed to that for too long. So it's the current that's dangerous. The actual amount of charge per second that you're getting through your body rather than the voltage itself. So when we're talking about current in the electrical circuit, it's really consisting of a few things. One of them is an electron pump, which is essentially your battery. Another thing is the consumer, or the thing that's doing the work, which in this case is the bulb. You also need something like conducting connections, which in our case is the wires that are actually hooking up the system. And you'll have a lot of electrical resistance in the battery itself and in the wires, but we tend to ignore that unless you're actually specifically told to. And that's quite true at short distances. We'll see that changing when we start getting to distances of kilometers for wires. And if I ever ask you, draw a circuit diagram, what I'm really not looking for is this. So if you draw a diagram of a circuit with a voltmeter and an ammeter, a voltmeter measuring voltage, an ammeter measuring current in this particular case, which have nearly universally been replaced by multimeters, which do both of these functions, but still, voltmeter here is a V, this is an A. And then we've got a bulb and a battery. If I say draw a diagram, I don't want this. I don't want to see a diagram that's a whole mess of wires with a couple of meters in it. A circuit diagram looks like this. And this is the kind of thing you need to learn to interpret, and the kind of thing you will see on exams and questions. So these lines here, these are a battery. These are a long line and a short line usually. This just indicates there's multiple cells. 3 cells here, which are probably 10 volts each for a 30 volt cell. Positive and a negative end, electricity with arrows flowing through it, voltmeter and an ammeter, and here's that bulb that's shown as a 15 ohm resistor. So that's what I want if I'm talking about a circuit diagram. So there's a diagram of a circuit, 2 resistances, essentially bulbs. This is breakage here, this is a switch, which is this switch, and here's the battery hooked up to the whole system. And there's some of the typical electrical symbols that you might see. Here's a battery. This is a resistor. Sometimes you might see a resistor still drawn like this. This is more of the old way of doing things, but still you might see this. I tend to do things as this squiggle. It just makes life easier as a shorthand when I'm actually drawing in my diagrams, but you might see either or of these. Same with a capacitor. We've seen many capacitors in the past, and I tend to use them as a double line like this. Sometimes you might see it as a line with this kind of semicircle attached to it. A switch, of course, we've already seen one of these, is a break in the circuit that you could imagine if you push this, you make the circuit. And any line otherwise is a piece of conductive wire. More symbols, just in case you were wondering, as diodes and fuses. We're probably going to restrict ourselves mostly to batteries, capacitors and resistors. If you're looking at a circuit, if you switch a circuit on, there's a lot of free electrons running around in there, and they're always moving in relatively random ways. If you switch on a circuit to on and pass it through a potential difference, essentially give all of the electrons a direction to move in, suddenly the random speeds are overcome and all of the electrons organize themselves at about the speed of light, or 10 to the 6 to 10 to the 8 meters per second. So we don't have to worry so much about these random losses in our wire, and just assume once we switch our electric field on, our electrons are all going the right direction. So when we close the switch of a circuit, we establish a potential difference and an electrical field in that circuit, and that causes electrons to flow away from the negative terminal and come over to the positive terminal. So as I said, when we switch our system on, we establish an electric field which propagates at about the speed of light, 3 times 10 to the 8 meters per second. Free electrons might still drift around, but generally all of our electrons are going the right direction. If we look into batteries a little bit, they go back quite a way. Ancient Babylon actually had batteries made these around 2500 BC. It's believed they were actually used for electroplating, in making metals look pretty and adding extra layers to metals, possibly for rust resistance. Incidentally, these batteries were actually housed in a museum in Iraq and have since been destroyed in various wars. Where the word volt comes from and where our voltaic cell comes from, the modern nomenclature at least, is by taking a solution to allow our electrons to move through, and then putting an anode and a cathode into that solution, and then essentially allowing the electron flow to go through this. Here we've got copper and zinc, and that's going to cause a potential difference in this acid solution, and that's going to cause electrons to flow through this system and then through these wires and power this device over here. That's the more modern system, rather than using enclosed clay pots. So here's our zinc electrode and copper electrode, and here's more of a diagrammatic form with our sulfuric acid electrolyte inside. That's the principle of modern batteries. Today we have much more complicated chemistry going on, especially in something like a rechargeable battery. However, we're not going to go down the chemistry road here. We really care about setting up a potential difference and making that potential difference mobilize electrons for us. If you really do want to see some of this in action, and it's very, very rare that I point to a work of fiction, in this case I will. If you go and watch Breaking Bad, for instance, I'm not going to talk about people making meth here. What I'm really talking about is one particular episode called 4 Days Out, where these two guys wind up stuck in the desert with a dead battery in their RV. And they basically use a lot of zinc and a lot of copper that they have lying around in their lab to build a new set of cells inside Tupperware to charge their RV and get going and get themselves back home. So if you ever find yourself stranded in the desert in a meth lab, you can find your way home based on this particular video.